Okay. Good day, we are Job Lozada and Andre Gabriel Llanes, and we are here to demonstrate our MP2, which seeks to create a C and assembly kernel that performs a dot product between two vectors and plays the results in S dot. This program mainly uses three files, as you can see here. Main.c, which mainly defines the C kernel and benchmarks in C. Dot product ASM for linking.asm, which defines the assembly kernel, as well as dot product sasm.asm, which also defines a kernel but also includes a self-contained demonstration program. These are basically do the same thing, but this one has additional functionality for benchmarks. So to start off at main.c, this program, the main.c file, again, mainly provides the C benchmark driver and also creates two dot product kernels and measures their correctness in performance, as you can see here in the main file. And so going up first, going over dot prod the kernels itself, the C kernel dot product C here uses SSC2 scalars and by loading a single double per iteration into A underscore M128D with an load SD, multiplies it with mol SD and adds it with add SD and stores it back into the scalar accumulator. This program also allocates 16-byte aligned arrays with aligned malloc and fills them with pseudo-random data. Yeah, and runs num underscore run iteration for three vector sizes: 2 to the power of 20, 2 to the power of 24, and 2 to the power of 28, and measures them using the query performance counter function uh, as we go over the various benchmark functions. After each kernel it prints pre-run per run timings, computes average times, compares the numerical results using fab seconds epsilon, and reports speed up. Main.c. So yeah, that rounds up the overview of what main.c does. Going over to the assembly file that is linked in this project, starting off with dot product ASM for linking. This is a minimal linkable NASM implementation of dot product ASM that intended to be assembled to a Windows 64 object. Use, I mean using C and assembly linking as shown here. This is the way this file is linked. Okay. It begins with bit 64 and default rel and exports a single symbol. Uh, the, the routine uses scalar SSE to XMM instructions X or PD XMM0. Particularly XMM0 zeros the accumulator, while MOVSD loads one 64-bit double from each array into the low lane of the XMM registers, and molSD computes the product in the low lane and and add SD accumulates the product into XMM0. RAX is used as an integer index and multiplied by 8 to form addresses. The function tests R8D to handle cases where n is less than or equal to 0 and returns with the scalar double left in XMM0. Moving on to dot product sasm.nasa ASM. This is an alternative to the previous file where other than the functional where it also includes a demo built around uh, the IO64 helper macros, and it contains a sample vector A, vector B vector size, .bss slot for s dot, and a cmain entry that prints messages calls dot product ASM, stores the return value with move sd s dot, xmm0, and prints result. It also includes a dot product ASM implementation equivalent to the linkable file, the same scalar loop and XML instruction sequence. So the file can run as a standalone assembly demo that performs the dot product and outputs the and outputs and prints the output without any C driver. Because the dot product uh, the ASM combines IO and kernel, it's useful for quick assembly only testing. However, if you plan to link a small kernel object into main.c, you should not include this file or any other object that defines .product ASM, since these both have these in the same link because both exploit the same symbol and will produce multi-definition linker errors. If you want the standalone demos printed output, use uh, product sasm.asm. If you want to do a C++ benchmark, use the more minimal product ASM for linking and add its .obj file to the Visual Studio linker outputs. So yeah, that's a brief overview of our source code.
So, hello, my name is Andre, and I'll be continuing on by showing you the execution of the project. So, starting it off, first I'll try to build, compile, and run the program. It will take a while, so I'll briefly explain how to set it up. So, as you can see, it successfully showed the output for 2 raised to 20. Then it's doing 2 raised to 24. Then 2 raised to 28 is going to take a while, so I'll briefly explain how you set this up. So on Dev C++ IDE, we first open the project and we click on the C project file. After that, you go to project options, parameters, linker, and you choose the, wait, hold on. And you choose the .product as an object. So basically, what happens here is that we must manually create this .product asm .object from .product as sasm .asm, and you can do that by running this command on your terminal. Since devc cannot run assembly programming language, so let's check the output. So it's still running. So let's basically check first yung output ng 2 raised to 20. So basically what we want to see is that the C kernel runs 20 times, the assembly kernel runs 20 times as well. Then we're gonna compare results for correctness where it should be identical. Then it will calculate statistics ng average tsaka yung speed ratio. So okay, as you can see, sa n equals 2 raised to 20, it ran 20 times for C. Then sa assembly, it also ran 20 times. And as we can see naman talaga, assembly is faster. So ito yung C result, ito yung assembly kernel result, and they're identical. So it passed the correctness. And ito yung average execution time nila. It's just a simple computation. Then ito yung speed computation nila. So assembly is definitely faster. So moving on to n equals 2 raised to 24. So ito yung execution ng C kernel, 20 times. Then ito naman sa assembly, which is faster again. You can see 0 yung first decimal place niya while C is slower. Yun. And as you check again yung results, it passed the correctness test. And ito yung average execution time niya. And it's again, assembly is faster. Then moving on to 2 raised to 28, did it finish compiling? And it finished. So for C, it runs 20 times again. And for assembly, it also ran 20 times again. And this time, assembly is again also faster. And we can see the results here that it again passed the correctness test and the average execution time. And as you can see, assembly is again faster than C. And that's basically it for the program. We tested it on n equals 2 raised to 20, n equals 2 raised to 24, and n equals 2 raised to 28.